There is a potential danger in space, and it's on a collision course with Earth.
It's still 7 years away, but scientists are already sounding an alarm.
The moon may seem like a quiet, lifeless rock in the sky, but beneath its dusty surface lies a mystery that could change space exploration. In one of its most perilous regions, where temperatures drop lower than on Pluto and where darkness has ruled for billions of years, scientists have discovered something baffling, a substance that shouldn't be there. It's a clue that defies expectations. Yet, every attempt to uncover its secrets only deepens the enigma. Why does it vanish when we approach? What invisible force is keeping it hidden? This discovery could unlock the moon's potential or reveal challenges we're unprepared for. Before we can take our next giant leap, we must first solve the riddle at the most dangerous place on the moon. The fascination with the moon and its mysteries. For centuries, the moon has captured the imagination of humanity, serving as a symbol of mystery, inspiration, and scientific curiosity. As Earth's closest celestial neighbor, it dominates the night sky, revealing its vast, cratered surface even to the naked eye. Despite mankind setting foot on the moon over 50 years ago, it remains a place of intrigue, with many unanswered questions about its origins, composition, and potential for sustaining future human colonies. However, exploring the moon is no simple task. Its harsh, airless environment and extreme temperature fluctuations make it an incredibly dangerous and challenging destination. Lunar surface temperatures can reach 127 degrees Celsius or 260 degrees Fahrenheit during the day, and plummet to negative 130 degrees Celsius or negative 202 degrees Fahrenheit at night, while the permanently shadowed regions, PSRs, near the poles can drop as low as negative 250 degrees Celsius or negative 418 degrees Fahrenheit, making them some of the coldest places in the solar system. Yet, scientists and space agencies worldwide continue their pursuit, eager to unlock its secrets and utilize its resources for future exploration. But beneath its desolate surface, the moon hides a secret that rewrote history. The first hints of lunar water. For much of human history, the moon was believed to be a dry and barren world. When astronauts brought back lunar samples during the Apollo missions, the soil appeared devoid of moisture, and any trace amounts of water found were assumed to be contamination from Earth. However, in 1976, the Soviet Union's Lunar 24 mission provided the first real clue that the moon might not be as dry as once thought. The robotic probe drilled 2 meters into the lunar surface and returned 170 grams of soil samples to Earth. To the surprise of scientists, these samples contained water, approximately 0.1% by weight, with higher concentrations detected at greater depths. Despite this, the discovery was not widely accepted, as it was still believed that any water must have originated from earthly contamination. In the 1990s, the search for lunar water gained new momentum with NASA's Clementine and Lunar Prospector missions. Clementine, launched in 1994, mapped the moon in unprecedented detail and identified permanently shadowed regions, PSRs, near the lunar poles, deep craters that had not received sunlight for billions of years. One of the most intriguing was Shackleton Crater, which scientists believed could act as a natural cold trap for water ice. This discovery was significant because such regions could act as natural cold traps, preserving ice for long periods. In 1998, the Lunar Prospector mission followed up on these findings, using a neutron spectrometer to detect hydrogen at the moon's poles. The data suggested that vast amounts of hydrogen, possibly in the form of water ice, could be buried inside craters at the lunar poles, with estimates ranging from 10 to 300 million tons. However, since hydrogen could also be present as hydroxyl, OH, rather than water, H2O, the question remained unresolved. In 1999, NASA undertook an audacious experiment to find out whether water existed on the moon. The Lunar Prospector spacecraft was sent to crash into a South Pole crater, hoping that, upon impact, vapors containing material with water ice would be blasted into outer space for telescopes to analyze. Unfortunately for the scientists involved, none were definitive signs of water. Other missions in the following years, and notably Japan's Kaguya orbiter in 2007, also failed to gather concrete evidence of ice in shadowed craters. For a time, It seemed that lunar water remained an unsolved case until some breakthroughs came with India's Chandrayaan-1 mission in 2008. Chandrayaan-1 revolutionized our understanding of lunar water by detecting it in a manner no other mission had before. Rather than relying solely upon distant sensors, this mission included an impactor that crashed into the moon near the South Pole, analyzing the ejector for water vapor. The data confirmed the long-in-search presence of water. In addition, Chandrayaan-1 carried NASA's Moon Mineralogy Mapper, M3, which used spectroscopy to detect water molecules across the lunar surface. This constituted the first concrete evidence that the moon was not completely dry, and indeed water, be it ice or hydroxyl, was more widespread than previously thought. This invigorated a renaissance in lunar exploration, with scientists and space agencies around the globe further investigating the moon's covert water reserves. Breakthrough discoveries of lunar water. The confirmation of water on the moon came after decades of speculation and inconclusive findings. While missions like Lunar 24, Clementine, and Lunar Prospector had hinted at the presence of water, no definitive proof had been found. This changed in 2008 with India's Chandrayaan-1 mission, which provided the first concrete evidence of lunar water. The mission's Moon Impact Probe, designed to detect water in its gaseous form, crashed near a crater at the moon's south pole and detected water vapor in the ejected debris. Soon after, NASA's Moon Mineralogy Mapper, M3, an instrument on board Chandrayaan-1, confirmed the presence of water molecules across the lunar surface using spectral analysis. This groundbreaking discovery proved that the moon was not entirely dry and set the stage for further exploration. Despite this major step forward, scientists wanted additional confirmation. In 2009, NASA launched the Lunar Crater Observation and Sensing Satellite, LCROS, along with the Lunar Reconnaissance Orbiter, LRO. LCROS was designed for a direct impact experiment, similar to Lunar Prospector's attempt a decade earlier. This time, however, the spacecraft carried instruments that would fly through the debris cloud to analyze its composition before crashing itself. When LCROS's spent rocket stage slammed into the moon's Cabeus crater, the resulting ejector was observed by Earth-based telescopes and LRO. The data confirmed the presence of water ice, as well as other useful compounds like hydrogen gas, ammonia, and methane. This was the first time scientists had direct, undeniable proof of water ice on the moon. The LCROS missions confirmed water presence in the permanently shadowed craters, but subsequent missions showed that the water may not be restricted to the dark regions of the moon. In 2020, NASA SOFIA, or Stratospheric Observatory for Infrared Astronomy, found evidence of water molecules on the exposed lunar surface in Clavius crater. This discovery was unexpected because scientists believed that any water exposed there would evaporate right away due to the absence of an atmosphere. Water was discovered in concentrations ranging from 100 to 412 parts per million in the lunar soil by SOFIA, although it is still much less compared to the driest deserts on Earth. These remarkable findings have altered our perception of the moon and triggered visions of its exploitation. Water on the moon would be a game-changer for human space travel, as it could provide drinking water, food production, and hydrogen and oxygen for rocket fuel. Excavating and utilizing this lunar water would lessen the amount of material that must be sent from Earth, making the case for long-term lunar bases and deep space missions. But how accessible will this water be? How will it migrate across the surface? And what extraction methods will work best? Shortly, new missions including NASA's Artemis program, China's Chang'e Lunar Exploration Series, and private space companies such as SpaceX, Blue Origin, and Intuitive Machines will return to the moon. And unlocking the lunar water potential remains a key topic for scientific investigation. How water exists on the moon. Water on the moon exists in several different forms, depending on location and environmental conditions. The most well-known and easily understood form is ice, which is found in permanently shadowed regions, PSRs, near the lunar poles. These areas, such as Shackleton Crater and Cabeus Crater, have not seen sunlight in billions of years, making them natural cold traps where temperatures can drop as low as negative 250 degrees Celsius or negative 418 degrees Fahrenheit. At such extreme cold, any water that reaches these craters whether from ancient comet impacts or interactions with the solar wind, remains frozen and preserved for millions or even billions of years. The Lunar Reconnaissance Orbiter, LRO, and the LC-ROSS mission provided strong evidence that significant amounts of ice are locked within these craters, though extracting it remains a challenge due to the extreme cold and lack of direct sunlight. However, water ice is not the only form of water on the Moon. Observations from NASA's SOFIA, or Stratospheric Observatory for Infrared Astronomy, in 2020 revealed that trace amounts of water molecules exist on the sunlit portions of the lunar surface, particularly in the Clavius crater. This was a surprising discovery, as scientists had previously assumed that any water exposed to the harsh lunar daytime temperatures, reaching up to 127 degrees Celsius or 260 degrees Fahrenheit, would quickly evaporate and escape into space. The key to its survival likely lies in how it is stored. Some of this water is thought to be trapped inside tiny bead-like structures called impact glass, formed by the high heat of micrometeorite impacts. Another possibility is that water molecules are sheltered between grains of lunar soil, regolith, protecting them from direct sunlight and allowing them to persist over time. The Moon might also develop water from the chemical processes engendered by the solar wind. The Moon's surface has a host of oxygen-laden minerals, one among which is plagioclase feldspar. In chemical reactions between hydrogen ions from the solar wind and these minerals, hydroxyl OH molecules, a close relative of water, are produced. The bombardment of the surface by micrometeorites over long periods may give further momentum to the transmutation of hydroxyl to genuine water molecules. It thus appears that lunar water acts like a non-static resource, being constantly generated and lost depending on solar activity, bombardment by micrometeorites, and interactions at the surface. This dynamic water presence means that astronauts on future lunars could look for alternative ways to obtain water from sunlit regions of the Moon, instead of relying only on frozen ice deposits in PSRs. Understanding how water exists on the Moon is crucial to supporting future endeavors of space exploration and colonization. If the relative lunar water cycle can be harnessed, it is expected to provide astronauts with a renewable resource that diminishes their reliance on Earth for supplies. However, scientists do not yet know how much water can be reasonably extracted. Some believe subsurface ice deposits may be more plentiful than superficial readings suggest, meaning future missions will have to dig to find larger reserves. Understanding how water persists on the Moon will thus be a prime step towards sustaining human life outside the Earth, as space agencies begin implementing long-term lunar missions. Challenges in extracting lunar water. Extracting water from the Moon presents numerous technical, environmental, and logistical challenges, with extreme temperature fluctuations being one of the most significant obstacles. Lunar surface temperatures can soar up in sunlit areas, causing water to evaporate before collection, while permanently shadowed regions, PSRs, experience frigid lows, making equipment operation incredibly difficult. Specialized drilling and mining machinery must withstand these extremes while efficiently extracting ice deposits. Another major challenge is the presence of electrically charged lunar dust, known as regolith, which is highly abrasive and clings to surfaces due to electrostatic charging from solar wind. Apollo astronauts reported that lunar dust stuck to their suits and equipment, causing wear and tear, and in shadowed craters, electric fields created by solar wind interactions could damage mining tools and even pose risks to astronauts. Managing this hazardous dust while preventing it from contaminating water reserves remains a major hurdle for sustainable lunar mining. If extraction efforts are complicated, it is where water ice is located and how accessible the ice is. Most ice deposits are confirmed to be in the PSRs, areas of permanent darkness where solar-powered operations are virtually impossible. While such facilities could be set up utilizing nuclear reactors or other energy sources, such as wireless power transmission, the logistical problems of setting up in such remote frozen conditions grow. The depth of lunar ice is also unknown. Some readings indicate that ice is mixed with lunar soil or is buried below the surface. Extensive drilling operations would have to be done. If water were dispersed rather than provided in thick sheets of ice, extraction would become vastly more difficult. On Earth, in such a case, liquid water is readily available. On the Moon, Ice will need special techniques to separate and purify. Financial and engineering hurdles are a must. NASA, ESA, and private companies like SpaceX, Blue Origin, and Intuitive Machines have all proposed various extraction methods, including heating regolith to volatilize water vapor or autonomous mining systems. However, these techniques need rigorous testing, and any failure could incur heavy losses. The recent cancellation of NASA's Viper, or Volatiles Investigating Polar Exploration rover mission, underscores the uncertainty and cost involved in lunar water extraction programs. Until reliable technology is developed for lunar water extraction, the dream of sustaining moon bases and deep space missions with lunar water will remain just a dream, making it all the more crucial that these challenges are overcome for the future of space exploration. Overcoming these challenges won't just unlock lunar water, it could reshape the future of space exploration itself. Importance of lunar water for space exploration. The discovery of water on the moon has revolutionized space exploration, offering the potential to support long-term human presence beyond Earth. Water is an essential resource for sustaining life, and having a local supply on the moon could dramatically reduce the need to transport it from Earth, lowering the cost of deep space missions. A steady source of water would provide astronauts with drinking water, sanitation, and even aid in growing plants for food production. Establishing a permanent lunar base, such as the one proposed by NASA's Artemis program, or China's ILRS, or International Lunar Research Station, would require access to a reliable water supply, making lunar ice deposits a critical asset for future missions. Without it, any long-term presence on the moon would be logistically and financially challenging, as transporting 1 liter of water from Earth to the moon costs approximately $50,000. Beyond sustaining human life, lunar water could serve as a crucial component in space transportation. Water can be split into hydrogen and oxygen through electrolysis, creating rocket fuel that could be used to refuel spacecraft at lunar fuel depots. Since launching payloads from Earth requires massive amounts of energy and fuel, producing propellant on the moon, where gravity is only 1/6 of Earth's, could make space travel significantly more efficient. Instead of carrying all the necessary fuel from Earth, spacecraft could refuel at lunar bases, enabling more ambitious missions to Mars and beyond. NASA and the European Space Agency, ESA, have both proposed using the moon as a stepping stone for interplanetary missions, with lunar water extraction playing a vital role in reducing mission costs and extending mission durations. Extracted and purified lunar water would benefit self-sufficient habitation in space. Perhaps more difficult in long space missions is the maintenance of a closed-loop life support system in which resources are recycled on an ongoing basis. Once again, water on the moon could be harvested and purified, used within habitats, and thereby not depend on the supply chain from Earth. Hence, this is a great step toward making space-based human colonies independent. The third utility of water is in shielding astronauts against radioactive radiation from the universe or space. Water could also hence be stored in a strategic location around living quarters to act as a second layer of protection against cosmic radiation and enhance the safety of astronauts in deep space environments. Thus, lunar water is important not only for exploration, it is an economically and strategically viable resource. More and more countries and private enterprises, including SpaceX, Blue Origin, and Lockheed Martin, are heavily investing in lunar missions, not only for the study of the moon, but also to stake claims on potential resources. The ability to harvest lunar water would likely offer future leverage on space exploration and commerce to any country with an active lunar program. The Artemis program by NASA, the pouring of sweat, blood, and mind by the Chinese Lunar Vision, and private companies trying to move ahead with lunar operations are all making this race for a sustainable water extraction technology urgent. Resources beyond water. The moon is not only a potential source of water, but also a treasure trove of valuable materials that could transform space exploration and industry. One of the most promising resources is helium-3, a rare isotope with the potential to revolutionize clean energy production. Unlike traditional nuclear fuels, helium-3 can be used in fusion reactions that generate power without producing harmful radiation or long-lived nuclear waste. While helium-3 is extremely scarce on Earth, the moon has been accumulating it from the solar wind for billions of years. Some scientists estimate that mining helium-3 from the moon could provide a nearly limitless supply of energy, potentially powering entire nations. However, the challenge lies in its extraction. Retrieving it requires heating vast amounts of lunar soil to release the isotope, making the process both technically and economically demanding. China and Russia have shown strong interest in helium-3 mining, with China's Chang'e program actively exploring its feasibility as a future energy solution. Aside from helium-3, the moon offers plenty of metals and minerals that are essential for supporting space infrastructure and the Earth-facilitated industry. The materials in the lunar regolith include iron, titanium, aluminum, magnesium, silicon, and calcium, which are important for building spacecraft, habitats, and electronics. Future mining technologies would allow the extraction of these metals for in-space manufacturing purposes, minimizing transporting heavy materials from the Earth. The somewhat exciting proposal concerns lunarcrete, a durable concrete-like substance made from moon dust that would construct radiation-deflecting shelters for astronauts. Similar rare earth elements, REEs, were also found on the moon, and their importance cannot be overstated concerning modern electronics, rechargeable batteries, and renewable energy technologies. Today, about 95% of the rare earth supply of the Earth is controlled by China, thus raising fears about global dependence. Given that mining on the moon can lower the degree of damage to the Earth's environment while providing a reliable means of supply for potential high-technology industries, this would allow alternative sources. Nevertheless, the legal plus economic issues about lunar resource extraction appear murky. Although the 1967 Outer Space Treaty prohibits governments from naming territorial claims on the moon, it is silent on commercial mining, creating a legal grey area. Nations including the United States, China, and Russia, as well as veteran mining companies such as SpaceX, Blue Origin, and Astrobotics, are already making serious preparations for mining the moon. Thus, international agreements will be critical to protect fair and sustainable mining practices. International lunar exploration efforts. The global race to explore and utilize the moon has expanded beyond a few leading space powers, involving multiple nations and private companies. The United States, Russia, China, India, Japan, South Korea, the United Arab Emirates, and the European Space Agency, ESA, have all launched lunar missions, each with distinct scientific and technological goals. NASA's Artemis program is spearheading the renewed push for human exploration, with plans to establish a sustainable lunar base at the moon's south pole by the 2030s. The successful launch of Artemis 1 in November 2022 set the stage for Artemis 2 in 2025, which will carry astronauts around the moon. Artemis 3, expected in 2026 or 2027, aims to land the first woman and the next man on the lunar surface, conduct extensive resource research, and prepare for future Mars missions. Meanwhile, China and Russia are advancing their lunar ambitions through the International Lunar Research Station, a robotic base planned for the 2030s, with human missions to follow. China's Chang'e program has already made significant progress, with Chang'e 4 achieving the first ever landing on the moon's far side in 2019, and Chang'e 5 bringing 1.73 kilograms of lunar samples back to Earth in 2020. Future Chang'e 6, 7, and 8 missions will explore the moon's south pole, where large water ice deposits may exist. China's recent collaboration with Venezuela on lunar research signals its growing space alliances and a potential challenge to NASA's dominance. With the confirmation of lunar water molecules by Chandrayaan-1, India has emerged as an important player in space, reshaping scientific understanding concerning lunar resources. The 2019 Chandrayaan-2 landing attempt failed. However, India's Chandrayaan-3 mission successfully landed near the moon's south pole in 2023, thus making India the fourth nation to soft land on the moon, and the first to do so in this crucial area. The Pragyan rover operated on the moon and gave fresh insights into the composition and temperature variation of the soil. Along with Japan's Selene Kaguya mission, the upcoming SLIM or Smart Lander for Investigating Moon project will embark on lunar gravity research and surface investigation, which also focuses on long-term strategies for automated and human missions. As lunar exploration speeds ahead, competition for resources is picking up. The Outer Space Treaty of 1967 prohibits any state from laying claim to the territory of the Moon, but it does not make provisions for commercial entities to be engaged in lunar mining, hence giving rise to legal grey areas. The Artemis Accords, championed by the US and signed by over 30 nations, promote peaceful cooperation, yet China and Russia are conspicuously absent, raising fears of geopolitical tensions. The unresolved mystery of lunar water. The presence of water on the Moon has been confirmed through multiple missions, yet its exact nature and distribution remain a mystery. Initial findings from orbiters like Chandrayaan-1 and NASA's L-Cross mission suggested that large deposits of frozen water could be trapped in permanently shadowed craters, PSRs, at the lunar poles. However, direct detection attempts by landers and rovers have yielded inconsistent or inconclusive results. For example, India's Chandrayaan-3 mission in 2023, which successfully landed near the Moon's south pole, failed to detect surface-level water, contradicting previous satellite data that suggested its presence. This raises key questions. Is the water hidden beneath the surface? Is it more scattered than previously thought? One leading theory is that lunar water is buried under layers of regolith, lunar soil, rather than existing as exposed ice. Data from NASA's Vikram lander, part of Chandrayaan-3, indicated that just a few centimeters below the surface, temperatures dropped drastically, suggesting that ice could be trapped beneath an insulating layer of dust. If this is the case, future missions may require advanced drilling technology or ground-penetrating radar to locate and extract it efficiently. NASA's upcoming Lunar Trailblazer mission, set to launch in 2024, aims to map the Moon's water distribution and determine how deep these deposits are located. Yet another theory could be that the Moon's water is not static, but goes through some dynamic, even if temporary, cycle. Observations from NASA's Lunar Reconnaissance Orbiter show that water molecules are born and die according to the lunar daytime, exposure to solar radiation, and interaction with the solar wind. One hypothesis utilizes hydrogen ions from the sun to react with the oxygen-rich minerals found in lunar soil to yield hydroxyl, OH, molecules, which over time convert back into water. The other variable attributed is micrometeoroid impacts, which may cause the ejection of water located in voids below the surface. Such conditions would allow for a transitory surface existence of water before being lost in space. If such a constant state of change prevails over lunar water, that could complicate the extraction of larger volumes, casting doubt on its viability for the long-term sustenance of colonies. Finding and extracting water from the Moon presents not only a scientific issue, but also a major determining factor for the success of any future missions. Water is essential for the survival of astronauts, to make fuel, and for sustaining lunar bases. If extraction turns out to be even harder than postulated, the mission plans would probably have to undergo a drastic change. The look at water ice deposits was delayed further after NASA cancelled its Viper mission. However, future missions from NASA and China, as well as some private companies, are poised to take an even deeper look at this subject with even more modern instruments and aiming for areas never really studied before. Unlocking the Moon's secrets is just the beginning. What comes next could change everything. The future of lunar colonization and industry. Lunar colonization is no longer just a dream. It is becoming a major goal for space agencies and private companies worldwide. NASA's Artemis program aims to establish a permanent human presence on the Moon, with Artemis Base Camp planned for the South Pole, where water ice deposits could sustain astronauts and fuel deep space missions. The first crewed Artemis landing, Artemis 3, is expected in 2026 or 2027, with plans for habitats, power stations, and mobility infrastructure to support long-term missions. In addition, NASA has awarded contracts to commercial companies, such as SpaceX's Starship lunar lander, to assist in astronaut transportation. The Lunar Gateway, a planned space station orbiting the Moon, will serve as a staging ground for future missions. Meanwhile, China and Russia are developing their own International Lunar Research Station, set to begin construction in the 2030s, with Chang'e 7 and Chang'e 8 playing key roles in testing in situ resource utilization, ISRU, technology for lunar fuel, water, and construction materials. China has also suggested its lunar station could welcome international partners, though its exclusion from NASA-led projects due to US restrictions has intensified competition between the two major space powers. The enormous mineral reserves of the Moon could nurture a space economy, superstarting human settlement. Helium-3 is considered an energy source of the future, and along with iron, titanium, and rare earth metals, could bring a complete paradigm change to industries on Earth and space. NASA has claimed that a single shuttle load of helium-3 could keep the whole US powered for a year, assuming they could mine and transport it. So lunar mining could, in theory, lessen the environmental footprints on Earth due to resource mining, but extreme weather, toxic lunar dust, and nebulous resource ownership regulations are hurdles to be overcome. Though the Outer Space Treaty of 1967 forbids territorial claims on the Moon, regulations on commercial mining are vague, thereby igniting potential geopolitical tensions. The 2015 Commercial Space Launch Competitiveness Act was passed by the United States, allowing American enterprises to extract and own resources from space. China and Russia are in support of pursuing an altogether new global governance scheme for outer space. The Moon's mysteries are far from solved, and the deeper we dig, the more questions arise. What do you think lies hidden in its most dangerous place? Let us know in the comments. If you enjoyed this journey, like this video, subscribe, and hit the notification bell for more space exploration content. Ready for more discoveries? Click on the next video now. Let's uncover the universe's secrets together.